Dear students, in the earlier sessions, you have studied about the properties of the union intersection. That is, there are three operations on sets. Now, we have learnt the properties of union and intersection after learning about the definition of union and intersection. Similarly, the third operation was difference. Now, in today's class, I am going to work out some problems connected with the properties of the sets. That means the distributive property or the associative property. I am going to work out problem. Then I am going to give the definition of another set which is called as a complement. Now look at this problem. Here there are three sets here. A is containing the elements 1, 3, 5, 7, B has 5, 7, 9, 11, C has 9, 11, 13. Okay. What you have to do is, you have to prove that A union B union C equal to A union B union C. Similarly, with respect to the intersection also. What exactly is this property called? It is called as an associative property. Associative means there will be three sets here. In whatever order you combine, it may be union or intersection, we will be getting the same result on both the sides. Now, let me start with the first part of the problem here. Now, on the left hand side, it is first one. Left hand side, what you have is A union B union C. So, I am considering the left hand side here. First, let me write the elements of A, that is equal to 1, 3, 5, 7. Union. Now, B union C, that is B is having the elements 5, 7, 9, 11. And this is 9, 11, 13. Since 9 and 11 they are common, you can write 5, 7, 9, 11 and 13. So, this would be equal to 5, 7, 9, 11 and 13. Now, again we are taking the union here. So, look here 1, 3, 5, 7. 5, 7 is present in the other one also. So, just write all the elements 1, 3, 5, 7, 9, 11, 13. So, these are the elements of the set we get on the right hand side, left hand side when you combine B and C, that is B union C, then combining with A. Now, let me start with the right hand side. What do you have on the right hand side? It is A union B union C. That means I am taking the union of A and B first, then I am combining with C. Now, what is A union B? 1, 3, 5, 7 and 5, 7, 9, 11. So, write all of them together. It is 1, 3, 5, 7. 5, 7 repeated, write only once, 9 and 11. Union, write the elements of C. It is 9, 11, 13. Now, union means we can simply write all the elements, which will not be a problem. But wherever the the elements are repeated, write only once here. So, it is 1, 3, 5, 7, 9, 11 and they are repeated here, no need to write again. So, these are the elements. What do you observe here? A union B union C, LHS has having 1, 3, 5, 7, 9, 11, 13. Same thing on the right hand side, combining A and B, then taking C together, we get the same elements. What does it mean? In whatever order you take the union, the value, the set remains the same. So, this is how we have to prove that one. So, usually such problems are given usually for a 3-mark question. Now, let me take the second part of that one. In this one, we are proving the associativity with respect to the intersection. So, here again start with the left hand side. What is on the left hand side? A intersection B intersection C. First write the elements of A 1, 3, 5, 7 intersection. Here you have to be careful. B is having 5, 7, 9, 11, C is having 9, 11, 13. We are taking intersection means the common elements have to be taken. What are they? 9 and 11 and 9 and 11. Write that one. It is 9, 11. Now, look here. We are taking the intersection of these two sets. One set is containing 1, 3, 5, 7. The second set is containing 9 and 11. And can you tell me what are the common elements? Do you see any common elements here? nothing is there. That means that we don't have any common elements, means what is the conclusion? It is a null set which can be denoted by 5. Similarly, you take the right hand side. Right hand side is A intersection B intersection C. Now first I take the intersection of A and B. Observe here 1, 3, 5, 7, 5, 7, 9, 11. So what is the intersection here? It contains only two elements 5 and 7. Now write the set C as it is, which is having the elements 9, 11, 13. Now again you observe here A intersection B is having two elements, C is having three elements. We observe that we don't have any element which is present in both the sets. That means in this case also it is a null set. Now this may not be case in all the problems here. In this one we are getting the intersection on both the sides, left hand side as well as the right hand side, a null set here, because in both the cases we don't have any common element. Hence we cannot get any element, means it is a null set or an empty set. So that shows that the union and intersection, the associative property holds good. That is, in whatever order you take the union, in whatever order you take the intersection, the left hand side would be equal to right hand side. Now in the next problem I am going to prove the distributive property. See, associative means the property would be same, either it may be union or intersection. But in the case of distributive property, two operations would be there, union and intersection, or intersection and union. Both of them should be proved here. Now let me take the next one. Here I am given the problem. If the set A contains 1, 3, 5, 7, set B contains 5, 7, 9, and set C contains 7, 9, 11, 11. You have to prove that, again two parts of the distributive property. First one is A union B intersection C. Whenever we think about the distributive property, there have to be two operations. If you take the number, addition and multiplication. When you take the set here, two operations, union and intersection. And how do you, what should be the answer? It is A union B. First I combine A and B. In between operation, intersection, it is A union C. Now the other way, here union and intersection. So what I am taking now is intersection and union. Two operations should be there. I have taken union, intersection here. Intersection and union. So how do you write that one? It is A intersection B union, this operation, it is A intersection C. So this is how you have to prove the result here. You have to show that the left hand side as well as the right hand side, they are equal to each other. Now carefully let us find the both the LHS, RHS one by one. Let me take the first one. Now first I take the left hand side, because in the right hand side there are two parts here. First I take the left hand side, arrive at a result. Then take the individual parts on the right hand side, take the intersection, then we will see whether they are equal to each other or not. So the left hand side is A union, it is left hand side equal to A union B intersection C. Now A means, first you write the set A, which is having 1, 3, 5, 7. Now union, intersection of B and C. B is 5, 7, 9. C is 7, 9, 11. What are the common elements here? It is 7 and 9. Correct? The common elements are 7 and 9. Therefore, we are taking intersection here. In between what you have here? Union. That means we have to take all the elements into consideration. 1, 3, 5, 7. 7 is repeated there. So, there is no need to write the 2 times the same number. So, this is the left hand side, which is having the elements 1, 3, 5, 7 and 9. Now, let us come to the right hand side part. What do you have on the right hand side? It is A union B intersection A union C. First we find A union B, then we find A union C, and we take the intersection of that one. A union B, 1, 3, 5, 7, 5, 7, 9. So taking the union, write in the form of a set only. 1, 3, 5, 7, 9. Okay. Intersection A union C, 1, 3, 5, 7 and 7, 9, 11. So it is 1, 3, 5, 7 and 7 need not be written again, 11. 7, 9, 11. So 1, 3, 5, 7, 9 is the union of A and B. 1, 3, 5, 7, 9, 11 is the union of A and C. We have to take the intersection of these two. Intersection means what are the elements should be taken? The common elements. What are the common elements? 1, 3, 5, 7, 9. All of them are present there. Therefore, the common elements, they become 1, 3, 5, 7, 9. And what you observe here? Left hand side, we had a set containing the same 5 elements. Right hand side, the set containing the same elements. That shows that the distributive property holds good. Actually, these properties are standard properties. You have to get the left hand side equal to right hand side. If you commit a mistake in any one step, you may not get the same elements. Then you can go back and check where exactly you have gone wrong, because the results should be equal to each other. These are all standard results which have been proved, and they have to be equal to each other. Now, let us try the other part of the distributive property, where we take the intersection first, then we take the union. So, let me move on to the second part of this one. That is left hand side. Again, it is A intersection B union C. First I am taking intersection, then I am taking union. That is, first write the set A. What is A here? 1, 3, 5, 7. Then intersection B union C, 5, 7, 9 and 11. 5, 7, 9 and 11. Now, in between we are having the intersection. That means we have to take only the common elements. What are the common elements? 1, 3, 5, 7 here, 5, 7, 9, 11 there. So what are the common elements here? It is only 5 and 7. So this is the left hand side. Left hand side is having two elements, 5 and 7. Now, let me take the right hand side. So what is the right hand side here? The right hand side is having, first I take the intersection A intersection B union A intersection C. That means that first here, first outside we are having intersection, inside it is union. So left hand side I took the union of B and C, then with A combined taking the intersection. Right hand side is individually I am taking the intersection A intersection B, then taking the union A intersection C. So first I have to calculate both A intersection B and then A intersection C. Now take A intersection C, that is this set and this set. What are the common elements? 1, 3, 5, 7. A intersection B means 1, 3, 5, 7, 5, 7, 9. So what are the common elements here? 5 and 7. So let me write it as set containing two elements, 5 and you have to use the flower bracket only. It has to be in the form of a set. Then union. Now A intersection C. It is 1, 3, 5, 7. And 7, 9, 9. So what is the common element? There is only one common element, that is 7. Now that means it is a singleton set here. Now in between what you have here? Union. Union means you have to take all the elements containing to both the sets here. 7 is repeated, you just take only once. Now this is what we are getting. So left hand side also we got two elements 5 and 7. Right hand side also we got two elements. That shows that the distributive property is true here. Now I told you already this commutativity, associativity, distributivity, all of them now they are all standard properties which have been proved earlier. Therefore, when a problem is given on that one, you were to ask for the verification or show that or prove that if they ask you, you have to get the same result. Sometimes if you commit a mistake in between, you may not get the left hand side equal to right hand side. Then immediately you go backwards and check where exactly you have gone wrong, and then you can correct it. Now, I move on to the next topic of the same set. It is called as complement of a set. Complement of a set. First I am going to give you the definition, and then we just I give you the definition as well as how to represent with the help of a Venn diagram. Now look here, whenever we think about the complement of a set, there has to be a universal set. Now let us consider universe. I have already given you the definition of a universal set. Universal set means it is the biggest set that is there for any discussion about the sets. Whatever may be the type of elements we are considering. Whenever you have a discussion about the sets here, we are considering some sets, the biggest among them, the same type of set which is the biggest among them, we call it as a universal set. So for all the problems, we cannot have a common universal set. That is, universal set is not universally defined. Universal set means it is the biggest in that particular type of elements here. Now here usually we denote it by capital U. Now let U be some universal set. Now let A be a subset of U. Let A be a subset of U. That means it is a part of U. Then the set of elements which are in U but not in A, that is the elements which are outside the set A, they form a set which is called as the complement of the set A. So how do you define the complement? The complement, let U be a universal set, A be a subset of U, then the set of elements which belong to U but not to the set A is called as the complement of the set A, and it is denoted by A dash. A dash means it is a complement. So how do you say? Usually the definition is asked, not by chance it is asked, you have to write like this. Let U be the universal set and A be a subset of U. Then the complement of the set A denoted by A dash is the set of elements of U which do not belong to the set A or which are not in the set A, and it is usually denoted by A dash. So how do you write this using the notation, or the set builder form? It contains all x such that x belongs to U and x does not belong to A. So this the set A dash is containing all the elements of U which do not belong to the set A, that is outside the set A. Now, or you can write in the other way also using the difference, it is U minus A. A dash equal to U minus A. So that is you take all the elements of U, take out the elements of A, the remaining elements would be, it is A dash equal to, you can write U minus A. Now let me give you an example here so that you can understand the definition carefully. Let the U contain, say, the elements 1, 2, 3, 4, 5, 6, 7, 8. Let A contain the elements 1, 3, 5, 7, some 4 elements. Clearly you can see that A is a subset of U. Now how do you write A dash here? Now just omit all these elements. See, apart from these elements, what are the other elements present? 2 is there, 4 is there, 6 is there, and 8 is there. So A dash becomes a set containing the elements 2, 4, 6 and 8. Now let me take another example here. Say, just to make the point clear here, 2, 4, 6, 8, 10, 12, 14. Let A contain the elements 4, 8 and 12. So I am taking 3 elements here. So you observe 4, 8 and 12, they belong to the set U. Therefore A is a you can clearly say that A is a subset of U. So what would be A dash? A dash will be containing the elements 4 is there, start with 2, 4 is there, omit that number, take 6, 8 is there, don't take that one, 10, 12 is there, omit that one, and 14. So the set A dash or the complement of A is containing the elements 2, 6, 10 and 14. Now you observe here, A is a subset of U, correct? Now 2, 6, 10, 14, these are present in the set A dash. You observe A dash is also a subset of U. That is, if A is a subset of U, automatically A dash also will be a subset, because we have taken the complement of the set A as the set containing the elements of U which are not in A, which do not belong to A. So A is a subset of U means A dash is also a subset of U. Now using the Venn diagram, let us see how we can represent that one. Now let me consider this to be the universal set U. Now let me take A here. A is a subset of the, I am not writing any elements here. Now A dash means the complement of A is the set containing the elements of U which do not belong to this one. That means that outside this one, the shaded portion. If you shade the other portion, omitting the set A here, now this becomes A dash. So the shaded portion will always denote the complement of the set A, which is denoted by A dash. Now similarly, as in the case of the union intersection, here also we are having some properties. Of course, all these properties I am giving the statement, they will not be asked for the proof. Only for the verification you will be asked to prove that one. Here first properties here, properties of the complements. Here first property is, we call it as complement loss. What do you mean by that one is, suppose you take the union of A and A dash. See, A is a subset of U, A dash is also a subset of U, just now I told you. A union A dash, then it would be nothing but the universal set, because the elements which are present in A will not be in A dash, the elements which are present in A dash will not be A. When you take the union of them, all the elements of A, all the elements of A dash would be present, which is nothing but the universal set. So we call it as complement loss. Similarly, if you take the intersection, A intersection A dash is a null set, because we don't have any element which is common to both of them. So we call them as complement loss. Next one is De Morgan's law. This is important, because important when I say sometimes in the examination they ask you to prove the results here. So De Morgan's law, here two operations are combined. There are two results here. One is A union B whole dash equal to A dash intersection B dash. You observe, first we have taken the union, then we have taken the complement. On the right hand side, we have taken the complement individually, we have taken the intersection. The other one is the reverse of this one. A intersection B whole dash equal to A dash union B dash. These two are called as De Morgan's law. It's an important result of the complement here. So first we take the union of the two sets, take the complement. It is same thing. It would be equal to the intersection of the individual complements. Here we have taken the intersection, then we have taken the complement. It would be equal to the union of the complements of the two sets. So these two are called as the De Morgan's laws. Now there are there are three more results. One is called as the law of the double complementation. The third law is called as law of the double complementation. What do you mean by that? Law of the double complementation means A dash dash would be equal to A. That is, when you take the complement, then again take the complement, it becomes the original set. For example, suppose it is like this. suppose U is having the elements 1, 3, 5, 7. Okay. Now let A has only 2 elements 1, 3. Now I am taking an example to show the result. Then what would be A dash here? A dash will be containing the elements which are not in A, that is A dash contains 5, 7. Now take the dash of A dash and take the complement of A dash. See 5, 7 is there, and what is the remaining element? It becomes again 1, 3. What is 1, 3? 1, 3 is nothing but the given set. That is something like this. When you add some number and again subtract some number, actually taking complement of complement 2 times the same operation, we get back the original set. So that is the meaning of this one. It is called as double complementation. So when a set is complemented 2 times, one after another, then we get the set itself. Now law of the empty set. Law of the empty set we call that one. That is when you take the empty set, take the complement, it becomes the union itself. See, empty set means it is not having anything. What is the complement of that one? It is a set containing all the elements. So we write phi dash equal to U. It is called as a law of the empty set. So what is the opposite of that one? Law of the universal set. Law of the empty set here, law of the universal set. That is, take the complement of the universal, automatically it becomes the null set, because universal set means it contains all the elements. When you take the complement, now it will not be containing any element. So this is the law of the empty set. This is the law of the universal set. So these are the properties of the complement of a set. So in today's session, what we have done, we have worked out problems connected with the properties of the union and intersection. Okay, the one is the associative property, the other one is the distributive property. Then we have learnt about the definition of the complement of a set, and we have expressed it with the help of a Venn diagram, and also we have learnt about the different laws or the properties of the complement of set. In the next session, I am going to work out some problems connected with the complement of a set. Thank you.